Welcome to Spirit Behind the Screen. Each episode, your host, Marty McCurdy, deep dives on industry trends around high reliability electronics and the supply chain in aerospace and defense. This is episode 63 with EPC's Alex Lidow with an update on GaN applications, roadmap, and reliability.
Hi, this is Marty McCurdy with Spirit Electronics and our podcast Behind the Screen. And today we have EPC with us and their CEO, Alex Lidow. Hi, Alex. It's been quite a while since we spoke.
Hi, Marty.
I think it's been 6 years if my memory serves.
That's right. Way too long.
It has been. First off, at that time, I was new to Spirit. We just celebrated our 7-year anniversary, but at that time I wasn't really, and I'm still not a big fan of social media, but I hear you have quite a following on social media, like millions of people. Is that true?
Oh, no. Oh, no, it's not true. I don't know about them, and that's even creepier, I guess. But
from a technology standpoint, I think GaN and what you do in the GaN industry, I think you have a few followers.
I think gallium nitride has gone from a curiosity to kind of mainstream in many industries, especially space, as a matter of fact.
Right. Well, that is what I want to talk to you about today is where is the GaN product? What generation are you on? What has changed over these years in the GaN? Because the industry, as you just said, like I see more and more silicon carbide and SiGe and GaN certainly is a little bit more commonplace than it was just simply 6 years ago. So I want to understand, what generation you're looking at now, what changes have come about, and maybe I know you have some great radiation data out there now. So kind of how you've evolved the product line into being a little bit more space friendly. I think it always was, but maybe it was a marketing effort by you.
So there's really, two tracks to that answer. One is the commercial GaN and the platform that we develop. And then the other one is the rad hard versions, which have been specially formulated for radiation hardness in space environments. And the commercial generation is about to get into the 7th generation. We certainly had a very long and interesting ride to this point. GaN started off as being better than silicon MOSFETs, commercial silicon MOSFETs, and now they're many times better than silicon MOSFETs. And we've expanded into automotive markets and into by the way, if you use ChatGPT or any AI, those electrons go through our parts. And solar and anything autonomous will use our stuff. So GaN really has, I'll say, the sweet spot for GaN has been anything new. Because when somebody comes up with a blank sheet of paper to do a new design, they'll find that GaN is better. Now, in the world of space, an inherently and properly conservative world, and it took us several years to get space legacy, people that would throw these things up in space. And now I think we on last count we have 200 and something thousand parts in various orbits from geosync to low Earth orbit, and we're also on Mars. So we've really been able to establish ourselves as a reliable technology and supplier to people who are, intrinsically conservative about what they do.
Great. Yes. Well, first off, ChatGPT is a no-no here at Spirit since we're a defense contractor. But I do know what it is, and AI for sure. We've got some AI wafers going through our test facility, so it's exciting. But let's negate the naysayers. When you say GaN is better, I agree, but that's because we use the products, we've tested them, we've done all kinds of interesting design wins with them. But what do you say to the naysayers on GaN, and why is GaN better?
In the world, there are naysayers that, first of all, concerned about new technology, so they are worried about the reliability of the product. I think all the naysayers now are, they say yay when it comes to the improvement in performance, the smaller size, and even in the rad-hard world, the lower cost of GaN devices. So the issue is reliability, and that's a very valid question. We've worked with so many companies now on establishing the reliability and also with our own work. And I will say one thing very definitively, and that is that the wear-out mechanisms for GaN will outlive all of us. And really the one thing to look out for when you do a design with gallium nitride is the same thing you have to look out for in silicon, and that's thermal mechanical stresses. It's the only thing that causes a failure, obviously other than a workmanship problem or something like that. Mm-hmm. And now with GaN, as opposed to silicon, we've eliminated the wear-out mechanism of radiation. And that isn't intrinsic to GaN. It was because we designed it that way. GaN starts off with some advantages like stronger chemical bonds and things like that, but it was our knowledge. And when I say our knowledge, my last engineering job was 42 years ago, designing the first rad-hard power MOSFETs. And so, I've lived through the world of space electronics from the beginning, and we understood what it took to do that from a device physics point of view. And so we did that. And our new 7000 series devices, which you have in spirit there, are made to be impervious to radiation. You can't fail them. That takes away not only a big fear from customers putting things in space, especially with the Europa debacle that we just saw, but also it allows you to reduce not just shielding, but you can also go to new topologies. We can talk about that if you like.
Great, I do. I want to touch on that only because I'm not sure I understand what new topologies are, but let's back up for a second. I just want to make sure you and I are talking about the reliability in the same way. I think, you and I have spoken about, the reliability again being incredibly high. Obviously, they're super small, which sometimes from a handling standpoint, but isn't the world getting smaller and smaller everywhere, right? Yeah. Super light, very cost effective. And the fact that you have space legacy, that was basic, 6 years ago, like we were talking, that was the challenge, right? Getting a couple people to fly these things. So the fact that you have 200,000 that you're flying now is just an incredible testament to what you've done in the industry as a whole. And when we started this year out here at Spirit, sometimes we compete with the big A's just from a distribution channel, but really we're very much like you. We're heavy on the engineering side, and we've expanded our engineering technology to include ASICs now and all these things, right? But at the end of the day, the reliability of these parts is what's key, and the radiation is the number one piece, right? Like, so the radiation testing that we do and getting anybody to fly these and get feedback or that that they're still operating up there is very key. Can you just on a short description kind of give us the levels of radiation that you've tested to at SEE or TID, or where are those kind of, I know the rad guys are probably wanting to know this if they don't know already.
So TID, total incident dose, is really gamma radiation. And, MOSFETs are 300K rad silicon for the really good ones. With GaN, there's no failure mechanism. So we've actually taken them past 100 megarads, and there's no failure mechanism. And that's because we don't have that thin interstitial oxide between the gate electrode and the channel. So write that off. That isn't there. Then there are two others that are typical. There's neutron, proton, and then there's heavy ions. Neutron and proton have mass as opposed to electrons, which don't have much mass. And therefore, they create displacement damage. In other words, they crack the crystal when they hit it. Right. Gallium nitride has much, much higher bond energy than silicon. So you get orders of magnitude less displacement damage. And so far, we've tested devices up to 10 to the 17th dosage with neutrons and protons without significant change in any parameters. And then there's single event. And single event is somewhat challenging because you have heavy ions that create a lot of displacement damage. I mean, you throw gold at 50 megavolts at anything, it creates damage. but you also have very high perturbations to electric fields. In silicon, when a heavy ion hits, it not only cracks the crystal, but it creates this huge cloud of holes and electrons that really creates an instantaneous short circuit in the device. If it hits the wrong place, it can actually crack the gate oxide and all sorts of bad things. With GaN, you still have the displacement issue, but as I said, that's much, much less than silicon. But we've organized the design of the device and the materials so you don't have the issue of electric field perturbations that cause short circuits. Everything goes up past 85 linear energy transfers, LETs. Mm-hmm. So just don't worry about it. You can't turn the dial any higher than that. So that's all you can see.
Yeah, no, that's fabulous. Really, really great. I think that certainly will attract the interest of people that are not familiar with it, right, to understand it. We've been on the, NGI and all these things, trying to get all the radiation data out there we can. It's the biggest conversation we've had this year. Again, coming back to how Spirit approached this year, we were really targeting, the engineering piece of the business, but we also moved into the new space market. So for us, the primes, we have a lot of penetration there. We are in the tier 2s heavily, but we really started to focus on some of the new space people. Have you been seeing a lot of attention from that market as well?
Yeah, I think it's fantastic. We've seen with SpaceX really lowering launch costs and rocket labs as well, that there's a lot more stuff going up into orbit, and a lot of it's going to low Earth orbit. That means that people frankly can use lower cost componentry because in low Earth orbit there's less radiation. So we are seeing a lot of that, and a lot of it is going with COTS. A lot of it is actually going pure chip scale, and that's fantastic. I think it's great. I think we have a space junk issue, but it's fantastic that people are using lower cost things to add services. And I want to bring up one little insight, and that is that gallium nitride is a power conversion component. It's used primarily in things like motor drives, like reaction wheels and satellites, and DC to DC power supplies. That's all a satellite is, really. It's a power supply that can be steered so that you can stick stuff on it and do things like take pictures or send transmissions and receive. So the value of GaN is in how well it can make a power supply in space. Yes. And so I think people are really understanding that's a big value add.
Yeah, it is. It's exciting too. We have what's called the kids corner now. So we're trying to inspire the, K through 12 to try to get employees later in life, right? So we have this idea of curriculum of helping them understand what a satellite does for them on a daily basis, right? You wouldn't have your internet or your iPad and all these things. But in that process, it's been super fun for us to look at, you're right, it's just a big power supply, but I love all of the data collection that's happening, right?
Fantastic.
It's fantastic. The maritime, trying to get a handle on all maritime and the forests and just the massive amounts of data collecting that's going on in space. I think is just an amazing time, to be in our markets. So I think the new space has a lot of attraction for the new kids coming around to jump into our industry.
Yeah, it's really been revitalized. I think that the consequences, we're going to have to deal with space junk, but the revitalization has opened up so many fun new things.
Yes, the idea of slingshot it around the sun and burn it up is still a good idea. I want to stay technical before I ask you a few other things. Let's talk about this new topography that you mentioned, because that's a new phrase in my world. So let's talk about that.
So as we said a minute ago, satellites are just power supplies in space. The more power they supply per kilogram, the more valuable they are. So the efficiency of the power supply is a very important thing. Now, if you have radiation sensitive components, you obviously have to shield it, and that adds weight. But the big problem has been with MOSFETs is that if a heavy ion comes shooting through, it creates a short circuit. Now, if you have a topology that is the most common terrestrial topology for power conversion, it's called a half bridge. and you have half bridges, you have full bridges, you have three-phase bridges, but they're a high side device and a low side device. And if a heavy ion goes barreling through that and it causes a short circuit, it will short circuit the power rail to the ground and things blow up. So that's unacceptable. The solution in space has been to use a much less efficient and older topology called single-ended flyback, where you have an inductor and a FET. So the inductor is not susceptible to heavy ions. So if you get a short circuit, the inductor will basically be holding back from making a short circuit and destroying the system. But because GaN doesn't have that failure mechanism, they can now go to the much more efficient half-bridge topologies, which I'll use VPT as an example. Their single-ended flyback was in the 80s of percent efficient. Their half-bridge is 96% efficient. So that, that's cutting the losses more than in half. And this really opens up a big new world of much more efficient, fewer solar cells. All that is possible now.
Amazing. I'm going to do a little homework on that one because it's new to me. But we do a lot of half bridge testing here for some crazy reason. So I'm going to see how that ties in. I appreciate the application specific conversation. I think GaN is still very heavy in LiDAR and the automotive side. So let's kind of maybe switch gears and touch that audience a little bit. So anything new and exciting in that area? Because everyone in Phoenix, where we are, sees Waymo every day, all day. And, you're so used to it now, you don't even realize that there's nobody in there, right? You're just comfortable with them beside you. Unless you're stuck at the red light and you go, no, you go first. No, you go. And then you realize nobody's in there. You can't see you like waving them in. So let's hear about what's happening on the automotive side of EPC.
So, EPC started off in automotive on headlamps, and, that's our first application, which is not a big one for us, but still there. And the next one was LiDAR, light detection and ranging, which is also a space application. And that's where you fire a bunch of photons, you measure how long it takes to get back, and that tells you how far away something is. It's the most efficient way to create a 3D image is LiDAR, because it gives you just X, Y, and Z. I say that because it's become ubiquitous in autonomous motion in general. Robots, delivery vehicles, drones, and autonomous or semi-autonomous cars. So say level 3 automation. Every level 3 automation car today has LiDAR on it, sometimes multiple LiDARs. I think that will continue to be a big factor. Surprisingly, maybe, it doesn't make me comfortable, is China is dominating that world now. They will build 1 million level 3 automation cars this year. They have the largest LiDAR companies in the world by far, and they're planning in 2 years to be building 3 million. So where I think that the advantage of autonomous guidance is moving towards China. And of course, I'm sure that's a concern. Back to the world of automotive. Automotive is not just LiDAR, but it's going to 48-volt distribution systems for mild hybrids and electric cars. We're now on some electric trucks that are using 48-volt distribution systems. Because it's higher voltage, it means that the wiring harness is much lighter weight, and it turns out that's significant, much lower cost. That also is being adopted much faster in China, second fastest in Europe, and last fastest in the US. And then there's the other things around it, like infotainment, which is going towards GaN because of the efficiency in audio electronics, and things like those USB PD adapters. Well, USB-C today, adapters in your car that charge your phone in forever. Well, now the next generation cars will have the high current USB-C PD ones that can charge your phones very quickly. That all involves GaN because it's a very small, tight space. So GaN, I say this without any question in my mind, is as sure as the sun comes up, GaN's going to be completely replacing MOSFETs in cars. It's just a question of when. They're better all the way around.
Yeah, no question about that. And I drank the, electric EV car Kool-Aid early on in Tesla's life, and I'm still a big fan. So I know, let's talk about the voltage just a little bit more. So is GaN still from a manufacturing or maybe just company roadmap, is that still divided? Like there's the 0 to 600 volt GaN and then there's the 600 to 1000 volt GaN, or is that line started to blur a little bit on technology on the voltage side of GaN?
So the way most people break it down, the market forecasters, et cetera, they'll break it down as being 200 volts to 600 volts, 200 volts down to 40 volts, and then 40 volts down to 0. So 3 segments.
Nice. Yeah.
Our initial focus has been the 200 volt to 40 volt segment. And that's where all our products are largely focused in there. The 600 volt segment tends to be AC offline. So that's what you see used in fast chargers, and things that plug into the AC line. I think that AC to DC power supplies in general.
Yeah.
And then there's the under 40, where so far GaN has not been significantly outperforming MOSFETs, significantly enough to take over large swatches of that market. And that's changing because our new Gen 7 is a dramatic step beyond where MOSFETs are in that market. To break it down just numerically, that entire market for MOSFETs is about $12 billion. 25% of it is in that 600 volt segment, and 75% of it is in the below 600 volt segment.
Nice. Yeah, I didn't realize that the 0 to 40 or in that 40 range was now its own like market space. I thought that, all GaN manufacturing was happening like in those 2 voltages. So thanks for that update. Speaking of your roadmap, what does the roadmap look like? How does it look like in the next year, 2 years? What's in the R&D hat?
EPC, I think in the last 12 months has come up with a startlingly innovative new way of approaching GaN transistors, and they will be reflected in products starting to sample in December. It's our Generation 7, and it really does significantly change the equation. It allows GaN to compete at much lower voltages. It significantly lowers the cost of GaN in general. So I think that, I've said for years, it's inevitable that MOSFETs will be replaced by GaN. This just accelerates it. In the space area, there's another big deal, and that is that we've launched integrated circuits. And I think that we know about MOSFETs and rad hard for years, but ICs are also there. They're needed to work with the MOSFETs, and they're actually a little flakier than the MOSFETs. So we've now introduced a monolithic power stage. That's a half bridge that includes its own drivers and level shifters and input logic. And that has become extremely popular among satellite manufacturers because it not only combines a lot of shrubbery, but it takes away these very expensive rad-hard MOSFET drivers and integrates into a tiny little device.
Yeah, that's funny. I'm going to use your word shrubbery. The same thing, this new space that we tackled, we're totally in line with where EPC is heading. We started to find companies, or actually I would say those companies found us, that we're heading also into this like module subsystem world, right? Both from a manufacturing capability, but also a distribution channel. So it works really well for us. Domestic manufacturing here in the US is that we have companies that, let's take Europe or even the US, Canada, maybe, where they have something for the new space market and they're manufacturing and they're trying to break into this market where now that they've engaged with us, not only can we do the manufacturing here, even if it's, board builds or final test or system level test or whatever, but then we're also the distribution channel. So where you have headed with this monolithic power stage part of the business and the IC, that's really in line with where we feel the world is going also. And I think we probably started that in our minds last year because we see a lot of what's happening in the Silicon Valley with wafer probe, right? We have that capability. So we see a lot of new chips And, you know, the military and space, they want to touch everything early at individual component level and all these things. But the commercial side, they've already gone to board level tests. Like they don't have that kind of time and patience to come to market, right? So I like the convergence of the commercial business and people like the SpaceXs of the world, right? Grabbing that commercialization and kind of escalating the road to space. I think that's how we get there quicker.
I agree. We are very well aligned on that one.
Yep. Very good. Well, Alex, I know your time is super valuable. This has been great to catch up on you personally and what EPC is doing right now. But the technology, you're always leading the charge. So it's been great for me personally to catch up and see what's happening.
Thanks so much, Marty. What a pleasure.
Thanks for listening with Spirit this week. Be sure to subscribe, rate, and review this podcast to let us know what you want to hear about in aerospace and defense. You can find out more about Spirit's value-added services and product lines at spiritelectronics.com.